Okay, we're gonna continue with the diagrams, but in order to do something a little more complicated, because what we have also far is just a simple beam with a couple of rods, but if we to put more rods, it gets too crowded on a simple little beam. So we're going to talk about compound beams. So we can make like a larger beam with more stuff. This compound beam is when you get like this one, two beams connected by a beam. That's a compound beam. You have two beams connected by a beam, right? So the only difference here is that you have to calculate the reactions, and it's not going to be as simple as before. Because what we have been doing for calculating the reactions on those beams is you just get the theory that we use for rigid bodies, right? Remember, you got a rigid body. So for a rigid body, you have three equilibrium equations to calculate reactions, right? Remember that? That's what we did in the previous classes. But this is not a rigid body. If you remove the supports, it can bend in the middle, right? It can rotate here. This can rotate with respect to this, so it's not rigid. That beam is not rigid. So, and how many reactions you see in that structure that you see there? How many reactions you see?
Three.
One?
No.
How many? How many reactions?
Three unknowns. Unknowns are just all.
Unknowns is the same as reactions in this picture here. So how many reactions here? In general, including the X, 3, right? Yeah, we are not going to talk about X here, but in general, this is 3, so we don't get confused. Remember, I said a rigid body takes 3 equations. So let's talk up in those terms. So you have 3 reactions here and 1 here, right? So you have 4 unknowns. So we cannot use the 3 equations for this because we don't have enough equations for the amount of unknowns that we have. If we say, okay, we don't have any force in the x direction, okay, we have 1 less unknown, but then we have one less equation, because then we have summation of forces in the x direction, summation of forces in the y direction, summation of moments equal to 0, right? If we don't consider x forces because there is no x forces, we lose this because there is the equilibrium in the x direction is fulfilled by the fact that there is no forces in the x direction, so we lose this condition. So we have only 2 equations for 3 unknowns, 2 here and 1 here. So we have 3 unknowns and 2 equations. Where can we get the other equation to solve this problem? If we cut here, remember that when you have a rigid body, you have 3 equations, so you can solve for 3 unknowns. And in a regular problem, you have 3 reactions that you can solve with those 3 equations. If you cut this here, now you have this and this, and you can have 3 equations here. In this is a rigid body, and 3 equations here. It means you have 6 equations, right? The problem is that as soon as you cut, you get 3 additional unknowns, right? So it's kind of like doesn't do any good to cut because you have shear, moment, and axial load. So you have 3 unknowns. So you gain 3 equations, but you also get 3 unknowns. So you don't gain anything, right? The advantage of something like this is that if this is a pin, when you cut here, there is no moment unknown. So you gain 3 equations, but you only get 2 additional unknowns. So you get 1 equation extra for you to use to calculate reactions. When you have a problem like this, you have a cut here, and there is a pin, and you have here 3 unknowns, right? 3 unknowns. This is the reactions there. You have another here. The original situation here in general is 3 unknowns here, right? Another one here, another unknown here. So you have 4 unknowns. unknowns, right? And only 3 equations for the whole thing. You have only 3 equations. Now you cut here. You still have your 3 unknowns here. 3 unknowns. You still have your unknown here. This reaction here, 1 unknown. 1 unknown, I'm calling the X the unknowns. And then since you cut into, you have now 3 equations here and 3 equations here. They are separated rigid bodies. So you get 3 equations. Yeah, wonderful. I have a lot of equations. I can solve everything I want. No, because you gain 3 equations, but you also get 2 unknowns here. This shear and also the axial load, right? And this is the same, and this is the same. So you get 3 additional equations, but you really gain because you got 2 additional unknowns. So you get 1 extra equation out of the exercise. You cut and then you get 3 more equations, but 2 additional unknowns. So you get 1 extra equation that you can use to solve the unknown that was too many in this scenario here. Here you have 1 unknown more than equations. Now here you have 6 equations, and you have your 4 unknowns that you have before, plus the 2 new unknowns, so you get 6 unknowns here. So you get 6 equations, 6 unknowns, so you can solve the problem. Okay, hope this makes sense. This makes sense. If you don't cut a pin like this, but you cut on a regular place, you don't get anything because when you cut, you get 3 more equations, but when you cut, you get also 3 more unknowns, so you didn't get anything. So when you cut at a pin, there is no internal moment, so there is 1 unknown that you don't get. You only get shear and axial load. So you get 3 more equations, but only 2 unknowns, so you gain 1 equation that you can solve for the original problem that was missing 1 equation. Now you have the equation that you need. Now you get 6 and 6. Before you have 4 and 3, you need 1 more here to get equilibrium here so you can solve it. But then making the cut, you get 3 equations additional, so you get 6 equations, and you get your 4 unknowns, you get 2 more unknowns, so you get 6 unknowns. So it's enough. Now it's 6 and 6 you can solve. All right? It's simpler than I made this conclusion. So let's do a little problem, a little example. Yeah, too much of a confusion. The trick is to make the cut at a pin, so you don't have 3 internal forces. You have only 2 internal forces, shear and axial load. There is no moment. All right, so how are we going to solve this? Well, we need to cut this in 2. Let's cut this in 2. Okay, I have the 2 pieces. In the original piece, we have, in general, 4 unknowns, 3 equations, the original stuff, right? Okay. I'm gonna put the unknowns on these diagrams here. I am going to replace the fixed support. You replace this by a reaction at A, a moment at A, and an axial load. I like to call it Fn. Well, let's call it, you call it Na, right? Let's call it Na. We by looking that there is no forces in the x-direction, you know that Na is equal to 0 very quickly, right? But just to leave it complete, what forces I have to put in here? What forces I have to put in here? Here. What forces? This is like making a cut here and separate the two. So what forces you get when you make a cut? Shear, moment, and axial load. But in this case, we don't put moment because this doesn't oppose resistance to the rotation, so there is no moment. There is no internal moment here because of the pin. You understand that, right? The pin doesn't oppose resistance to the rotation, so the pin, the connection here doesn't apply any internal moment. So if you want to rotate it, it will rotate it freely. There is no moment right there. So the only forces here are shear at C. And I'm gonna because we know from the original the complete structure there we know that NA is 0, so let's get rid of that NA and we don't make any more mess here. But in general, if there is horizontal forces, there should be an axial load here, right? No, I'm not gonna put it because we don't consider it because in that diagram over there we see that there is no forces in the x direction. So that will be the only force at this connection. Anchored shear at C is kind of that. The pin is avoiding the beam to go like that. Is avoiding the beam to break in this direction. So that's an internal shear at the pin. So we have the same here, right? That would be like the forces at the pin. So I have to put it here in the same direction. And I'm going to replace the support at D by the corresponding forces. So I have to put here a force at D, reaction at D. Okay? I put only one because this is Rowley's. Right? So we can we solve these diagrams? Can you solve these diagrams? How many equations can you use here? In theory 3, but we discard already the x, so it's only 2, right? The x is gone. So, and we have to announce, so we should be able to solve this, right? We do moments about this, you get this, moment about this, you get that, right? Or moments about this, you get that. Can you solve for this one? How many equations do you have in this diagram? 3, because of the x thing, only 2, right? Forgetting about the x direction, how many equations will remain here? 2. And how many unknowns we have? This is not known, right? Reaction. This is not known, right? It's reaction. And this is not known yet. So this has 3, so we cannot solve this part. Once we get this, we can solve it because then we remain with only 2, so we can solve it, right? So here you see that you have to start here because here you have 2 unknowns and this one you can solve it. 2 unknowns, 2 equations. So you solve this, you get these values. When you have these values, you put it here and then you can solve this with the 2 equations of this diagram, right? So you have to check, you separate it and you see where can I start? I cannot start here. Or if you don't do that, if you don't do that, you call this and you start working, oh I got stuck, so you have to jump to the other one and continue. And once you have everything here, you can come back here. Alright? So let's do it. So you might call this free body diagram of CTE. Summation of moments at C equals to 0, positive like this. So that will be RD times 5 minus 10 times 10 equals to 0, right? So RD equals to 100 divided by 5. 20. Positive, so I got it right. So RD equals 20. I have a 20. Now summation of this is such a simple thing that I'm gonna do just let's do it last one. Summation of moments about any other point. What point you like here? I will do D, right? 0 positive like this. So V sub C times 5 D plus 10 times 5 equals 0. So V sub C equals minus 50. What?
Oh, no, sorry.
Problem?
No.
Everything correct? This is 10 minus 10, right? Minus 10. Oh, what does this mean? That minus, what does that minus mean? It's in the wrong direction, so I have to correct it, right? So you put a little note here better if you put it in another color, so you say, no, this is not right, this is like this, and it's 10, right? Not like this, and then we put it directly here, so here, because we are going in that direction, so we need to correct it here also, so this is not like this is like this, 10, right? Action reaction, all right? Clear for everybody? So now we can solve this because now we have only two unknowns, right? This one and this one, because this is already known. So you have two unknowns, two equations. The x direction is gone from the first. I'm gonna erase this so my diagram is easy. So now we have a free body diagram here. Free body diagram of ABC. What do you want me to do first? What would you do? Summation of moments at A equals to 0. I will do positive in this direction. So I have moment at A plus 40 plus 10 times 14. That's it, right? Because RA times 0, so equals to 0. Moment at A equals to minus 40 minus 140 minus 180 minus 180 negative. That means I had it in the wrong direction, right? So it's in the other direction. So let's put a little note here. So this is not like this. This is like this, and it's 180, and this is point A here. Okay, now what would you do? Yeah. Summation of forces in the y direction equals to 0. I will do positive going up. And then I have RA plus 10, right? Equals to 0, that's it. So RA equals to minus 10. So I had everything wrong today. I woke up with the left foot. So this is going down 10. Okay, we have all the reactions. So we are ready for the diagram, right? So let's put again the whole diagram here to start the diagram. So I put here copy. So let me put the reactions here. So here we have reaction. Reaction here is going down, right? And it's 10. and we have a moment that was clockwise 180. 180. And we had a reaction here at D. And reaction at D was 20. 20 going up. 20 going up. 20. Anything else? That's it. Okay, so now you put your auxiliary lines for the diagrams. You put your labels. Bounce. And then the chuku. Right? That part is fast. That part is easy. Right? What do you do? Chuku, 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 chuku. Boom. What do you do here?
Go down 10.
Go down 10. So I have to put some markings here. Let's do 2, 4, 6, 8, 10, minus 10. So this goes down minus 10. Remember, I want to hear everybody whistling and chuku during the exam. So I know that you are doing it, not you are not copying your partner, you are doing it yourself. Now, what do I do?
Just
Go horizontal because there is no forces telling you to move, no arrows telling you up to where, up to here, all the way up to here, because this is not a load, so this is shear. So the moment goes here, down here. So horizontal all the way up to here. Horizontal all the way up to here. Boom. Well, you see, all the way. And then here go up. Oh, and do this. So I see that you are doing stuff. So you go minus 10 plus 20 equals 10. So you go up to 10. So let me put the lines 2, 4, 6, 8, 10. This is 10. This is 6. This is minus 6. So now you go up 10. Now you continue horizontal. Boom. So you get 10 minus 10, 0. So you go down 10. Easy. Now a moment. So this is moment, pound feet, and it will be 40, 80, 120, 160, 200. $40, 80, 120, 160, 200. Okay, so how do I do this part here, starting here? Oh no, it's starting here, no. You have to look at the original thing. So what do you have to do here? According to the diagram here. What do we do here? You have this moment, right? So what do you do when you get a clockwise moment? Go up, right? The clock's above, the counter is below. So you go up directly up to 180. That will be up to 180, like that. This is 180. Now what do you do? Now what do you do here? Go down because there is negative area to add to this integral. This is the integral of this. The area here add to these values here. So we should get down here at a point that is this value minus this area. So let's put that area 1. I'm gonna do the area 1 up to here. Area 1 will be minus 10 times 8, so minus 80. So I have to do 180 minus 80 equals 100. And I go straight line, right? A straight line with negative slope, because that's what this number minus 10 is telling me. That all these points here have a slope of minus 10. Same slope. And it goes down to the point 100. So 100 is over here. 100 is gonna be, actually, it's like over here. 100. So this is gonna be a straight line here. And this is 100. Now what do you do? Go down, right? Again, counterclockwise. Now the counter is below, so you go down 40. So you have 100 minus 40 equals 60. So you get down up to 60. 60 is over here. And you put the number right there, 60. And now what do you do? Keep going down, right? This is a negative area here. Negative area. I'm gonna put this area 2 is all this area. Area 2 is all the way from here to here. So area 2 is equal to minus 10 times 6 plus 5. So this is 110. So I am at 60 minus 110 equals minus 50. Minus 50. So you have to go down all the way to minus 50. 40, 80, 40, 80. So let's see, minus 50 should be, this is 60, 50 will be somewhere over here, right? This little dot here is 50. So we go from 60 to 50 here. Okay, so this will be your minus 50. Minus 50. And now you go up this area 3. Area 3 equals 10 times 5, 50. So 50 minus 50 plus 50 equals to 0. Great. And now how do you go up? With the same slope, a slope of 10. So this is a slope of 10. And you see that if you go from 50 vertical and 5 horizontal, a line like this goes with a slope of 10, right? 50 over 5 is 10. So this line is a slope of 10. So let's do the portion right here. 0. Okay? All right? You see? What happened with the shear at C? Look. Remember the shear at C? Did we do anything with that here? Shear at C. This shear. Remember that we found that the shear here. Let's check. Is the shear at point C equals to? Actually, that shear is positive or negative? The shear is positive or negative? Negative, right? Makes this counterclockwise. Counterclockwise. It's just a check. It doesn't. Nothing happens. But look, the shear at point C is minus 10. See? Automatically. If you get that, you don't get shear minus 10 that as you got here, then it should be wrong. Something wrong. Automatically, you see that the shear at this point is what we found. And another thing that we can check is that the moment at the pin has to be 0. The moment at C, there is no moment at C, right? No moment. No. In other words, the moment is 0. Look, Huh? Nice. Good. And we didn't even think about that when we were doing it, but the moment has to be 0 at the joint. All right. Put those notes in your notes. Okay, let's do another problem. But you do it. I'm tired. Okay. Okay, so we have to break this in two because look, how many reactions we have here? Let's forget about the X break. How many reactions we have? Yes? 3. And how many equations do we have in general? 2. We forget about the X. So we need one more, right? We need one more equation. So then we cut it here and we get 2 plus 2. Now we got 4 equations. We have 3 unknowns. But here we're going to incorporate one more unknown. So now we have 4 unknowns and 4 equations. So let's break it. And let's break it. So now we put the reactions. Reaction at A. Reactions at C. And reaction at D. Reaction at D. What do we put at B? At shear. No moment because this is a pin. And that's why we break at the pin. Because we have one unknown less. Okay, let's put the shear here at B. Shear at B. And here on the opposite direction because it's action reaction. Shear at B. I guess we have everything ready. So, is there any restriction to starting in either one of them? Can it start here like before? We have 3 unknowns, and we only have 2 equations, right? So we cannot start here. We have to start here with only 2 unknowns. We have 2 equations. Free body diagram AB. Well, you do it. I cannot help it. What I have to do? Summation of moments about A equals to 0, positive like this. Summation of A. So I have, okay, B, so B times C.
Resulting of the triangular.
We have to do this, right? We have to do this trick here. Replace that triangular by an equivalent concentrated because for reactions we don't know what to do with all those things, right? But everybody knows the area of the triangle and everybody knows where it's located. It's 1/3 from which side? Or 2/3 from which side? 1/2 of 3 times 6, so 9. And this distance is 1. No, 2. It's 1/3 of 6. 1/3 of 6. Okay. So here will be B sub B times 6 minus the triangle is 9 times 1/3 of 3 is 2 equals to 0. So VB equals to 1/6 times 18. So this is equal to 3 positive. 3 positive. So I got it in the right direction. So it's 3 in the right direction. So I put the 3 here. And I put it on the other side also 3. So I have it ready for the next. And then reaction at A. Why do I calculate reaction at A? Do I need it? Now I have this already, so I can come here, right? Do I need reaction at A? For the diagrams, we need all the reactions for the diagram. So we don't need it here, but we need it because we are going to do the diagram. So for the diagram, you need all the reactions. Summation of forces in the y direction equals to 0, positive going up. So reaction at A, positive, minus 9 for the triangle, plus 3 for the shear equal to 0. So reaction at A equals to 9 minus 3, 6. So reaction at A equals to 6. Okay, now let's go here to free body diagram BCD. Summation of moments at C. Moments at C. Oops. Moment at C equals to 0. Positive like this. So RD times 4. Right? Oh, you tell me what? You tell me. You tell me what I have to do here. RD times 4, what else? Minus what?
Minus 4.
Minus 4, yes. What else?
Minus 5 times 2.
Minus 5 times 2. What else? Plus 3 times 1, right? Equals to 0. Reaction at T equals 1/4 of 4 plus 10 minus 3. So equals to 2.75. 2.75. Now, summation of moments about point D equal to 0, positive in this direction. RC times 4. 10 minus 4, right? What else?
Minus 5 times 2.
Minus 5 times what?
2.
2. And anything else?
Plus 3.
Plus or minus? About point T. Plus or minus?
Minus 3 times
Minus, right? Minus 3 times what? 5. Okay, equals to 0. Move it. RC equals to 1/4 of 4 plus 10.
Shouldn't the 4 be positive?
Yeah, let's see. Which the 4 is for the moment about point D.
And about point D.
Yeah, 4 is positive, right? And then what? RC around D is positive. The 4 is positive. Yeah, 4 is positive. The 5 is negative, right? And the 3 is negative. So that's correct? So now we have 4 is negative, right? Minus 4 plus 10 plus 15. So what do we get here? 5.25. Let's check a summation of forces in the y direction just to check. So we have, let's put it here. RC positive, so 525. 525. And RD positive, so 275. 275. So we have minus 3. I'm going to do positive going up here. So minus 3 plus 525 minus 5 plus 275. Will that give you 0? Really? Does it? Does it? Does it? 7, 8. Yeah. Equals to 0. This happy face, right? Okay, great. So let's put all our stuff. We have all the reactions already. So let's put all our reactions here on the original diagram. Let's make a copy down here. A 6 C, oops, C here. How much was C? It's 525. D. What is D? 275. Going up? I guess it was going up, right? Okay, your lines. Okay, so what do you do at the beginning? How do you start? Chuku chuku, exactly, chuku chuku. This is kilonewtons. Well, at the beginning, we start with a because we start with 6, right? So going up, directly going up, 6 going up. So let me put some lines here. So let's put 2, 4, 6. So you go up, you chuku 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 chuku, boom, 6 up. Okay, now how do you go down? How do you go down? Show me with your hand, like this, like this, like this. Is that a question?
No,
or
it's not.
stretch? Like this? Like this? What do you think, Mary? Like this? Like this, right? It start going down really fast because the arrow is big, right?
Yeah.
And then 0, so horizontal at the end because here there is no arrow at the very end. So it start down really quickly and then 0 here, right? But at what point here? We need to calculate at what point. We are not going directly to 0, we don't know that. So how do you know at what point you get here? Huh? The area. Let's calculate this area. Well, we have it right over there. Is the load of the triangle? What was that? 9. So we have to go down 6 minus 9, right? 6 minus 9 minus 3. So we have to go down all the way to minus 3. Minus 2, minus 4, minus 6. So minus 3 will be over here. So we have to go down like this. Faster at the beginning, slow, and then horizontal. Look at that. This like straight line is a defect of the software. Does not mean I did it perfectly cured, but this looks ridiculous. Made me look back. Such a nice trace that I did. Now what do you do?
Just go straight.
Just go straight. There is no loss in this little region. There is no loss, so you go chuku chuku, right? Chuku chuku, that little space here to one chuku 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 chuku, and then boom, 525. So we are at minus 3 plus 525. What do you get? 225, right? 225. 225 will be, this is 3, this is 2.5, so it's over here somewhere. So look, put the numbers, right? 225, don't forget the number. This was minus 3 down here. And now you keep horizontal, there is no loss, so chuku, chuku, chuku. Chuku, 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 chuku. Boom, you go down, 225 minus 5, what is that? 2 minus 275, 275. So, so you go here down, 275 is over here, this is 3, 275 will be over here. So, minus 275, and then you go horizontal, boom, 275 up 0, right? Boom. Minus 275 plus 275 equals to 0. 0. Great. Wonderful. Okay, now, moment in kilonewtons times meters. So how do you start here? How do you start here? Up, down. If you want to put the arrows, if that helps, you put these arrows, remember, if that helps, right? But the arrows don't go towards the beam, but away from the beam, and that will eventually help you, right? So here those arrows tell you to go up, right? Go up very fast at the beginning, and then 0 here, and then increasingly down, right? So it will be something like this. We need to work out the numbers, but it will be fast at the beginning, 0 right here, right below the 0, right 0, and then down, and then faster, and now we need to work out the numbers. That's hard, right? What? That's hard, right? We don't have the area. We don't have the area of this. What do we do here? What do we do? Right? Well, we can work the equation of this with the method that we checked a couple of classes ago, that we do the equation of the shear and the moment by making a cut, and then we have the equation of this line. When you have the equation, the rest is history, right? You just graph it with Excel, or you solve in the equation for shear, you solve for a shear equals to 0, and then you get this distance, right? You have to combine the methods when you have something that complicated. So let's get the cut here. We are going to do a cut here to find the equation of shear, because we need to find this. This is a very important point because it's the maximum moment. So we need this distance. We need this distance. So remember, let's do a review of that method. So we do a little cut here, where you have shear of at x, and then you have a load like this, right? Where this is 3 kilonewton meter, and this is W of x, right? And this is 6, and this is x. Remember that? Do you remember? We saw like a couple of classes ago, right? Okay, so you do summation of forces in the y direction equal to 0, positive like that to make it easier for our equation. So I have V of x plus, we need W of x, right? Okay. How do you get W of x? It's a straight line with intercept of 3 and a slope, negative slope of 3 over 6, right? So the equation is 3 minus 3 over 6 is 1/2 times x. That's it, right? The equation of W of x is 3 intercept and minus a slope of 3 over 6 is 1/2 x. That's the equation. So now we need this force. You can do the triangle and the rectangle, or you can do the area of the trapezoid. You know the area of the trapezoid? You don't know it? You don't know it? Okay, then you have to do rectangle and triangle. But if you want to know the area of the trapezoid, because could be useful, the area of the trapezoid is this. You should do it. Imagine that the area of the trapezoid is just a rectangle here in the middle. That's how you see, because this little triangle balances this one, so it's the same as a rectangle that has the same base, but the height of the rectangle is the average between this value and this value. So the area is B, the area is the big, let's say this big of B and little b. The average is B plus little b over 2. That's the average height. The average height of the trapezoid. You just multiply by the base. The base in our case is h, but just for the general equation, this, let's call this h. That's the area of the trapezoid. The average of this big and little side multiplied by the base. So, and that's what I'm gonna use here, because I don't want to break this into triangle and rectangle. But if you need to do that, well, you need to do that. Plus the area of the load, that will be the trapezoid, which is the big base 3 plus the little base, this expression here, 3 minus x over 2 divided by 2 times the height corresponding to this h will be this x here, x. And then what else goes into our summation of forces in the y direction? The 6. The 6 is going negative because we have positive going down, so it will be minus 6. So our equation of shear, V of x plus 3 over 2x plus 3 over 2x minus x over 4 square minus 6 equals to 0. So V of x 3 over 2, that will be 6 over 2 x minus x squared over 4 minus 6 equals to 0. Then our equation of shear will be equals to x squared over 4 minus 3x plus 6. So that will be the equation of shear. So now we need to solve this equation for when shear is equals to 0. So 1 4 squared minus 3x plus 6 equals to 0. So x will be equal to 3 plus or minus the square root of 9 minus 6, 3 divided by 2 1/2. So this will be equal to 6 plus or minus 2 square root of 3. We have 9.464 and 2.5353059. Okay, we just found the location at which the shear is 0, but why we found two locations? Let's take a look at that. This is actually the location of the zero crossing of a parabola, which is the shear diagram. This parabola here, this parabola goes like this. So it crosses 0 here at 9 point something, and it crosses 0 here at 2.5. This 2.5 is the one that we are interested, because this is where the moment is going to be maximum. We don't care about this other solution. So let's find the shear diagram, the moment diagram. We have to find now the moment diagram. We need to find the maximum value of the moment here, and we should verify that this value here is 0. We should verify, we can verify our equation with that value because we know that there is a pin here. So the moment has to pass by 0 in that point, and this moment is 0. We know because the moment starts at 0. There is no reaction moment on point A, so we know that the moment starts at 0. So let's develop the equation for the moment. We're going to do that based on the shear equation by applying the integral. Let's make a little cleaning here. Moment equation. So we're going to integrate this equation. Moment of x is equal to integral of v of x dx. So moment of x, so this will be equal to integral of 1/4 x squared minus 3x plus 6 dx. So this is equal to 1/4 x cubed over 3 minus 3x squared over 2 plus 6x plus integration constant. We know that the moment is 0 at x equals 0, so we can use that value to get that constant. M at x equals 0 is equal to 0 and is equal to 0 cubed over 12 minus 0 squared over 3 halves plus 6 times 0 plus c. So c is equal to 0 because all these terms goes to 0. So the equation of moment becomes c is 0, so we get x cubed over 12 minus 3 halves x squared plus 6x. That's it. So that's our equation of moment. Let's verify that equation gives us a 0 value at x equals 6. Here has to be 0. Let's verify that. Moment at x equals 6 equals to 6 cubed over 12 minus 3 halves 6 squared plus 6 times 6 equals to what? Equals to 6 cubed over 12, 18, minus 3 halves of 36, 54, plus 36, 36, 18, 54, 0. Good. So our equation goes through 0 at this point. Wonderful. And it goes to 0 at the beginning. Let's calculate the maximum value of the moment here by replacing the moment for x equals 2.5359. Let's put it here. M at x equals 2.5. I'll use the 5 figures in the calculator. So this is equal to 2.5 cubed over 12 minus 3 halves 2.5 square plus 6 times 2.5 equals 2. Let me put all those numbers in the memory. 2.5359 store A, store A, store A. No, couldn't do it. Okay, so now recall A cube over 12 minus 3 over 2 times recall A square plus 6 times recall A 6.928. 6.928. So that will be the moment maximum. Moment maximum will be equal. So let's draw it a little better here. So it has to go through this point here, start at 0, has to go all the way up to 6.92, so that will be almost 7. Here where the shear is 0, so it will be something like this point here, and it goes through 0 at the pin. Let's go down the pin. Okay, so this is the pin, so that's 0 also over there. Well, let's get rid of that. Okay, let's try to do the drawing. So it has to start with a lot of slope, then reduces until you get a 0 slope here, and then increases. That was an awful drawing, but that's kind of the idea. Okay, so we have here 6.93. 0 here, and then we have to add this negative area here. Let's call it area 3. We never calculate this area 1. We didn't calculate this area 2. Well, we can calculate area 3 because area 3, let me get rid of all this stuff a little bit to the side. And then we have that we are in this area 3 is equal to minus 3 times 1, so equal to minus 3. So we start at 0 here, we go to minus 3, so this will be minus 2, minus 4, so minus 3 will be here, so this will be a straight line. Now we go for area 4. Area 4 will be equals to 2.25 times 2, so that will be 4.5. So we go now straight from minus 3, plus 4.5 equals to 1.5. So we have to go all the way to 1.5 somewhere over here as a straight line. So we are here at minus 3, and here we are at 1.5. And then we have to go with area 5. Area 5 is equal to minus 2.75 times 2. 2.75 times 2, so 5.5. 5.5. So we go from 1.5 minus 5.5 equals minus 4. So we go all the way down to minus 4 here. Minus 4. And now we have a moment in the clockwise direction here. Means that we have to go up. The clock is above, the counter is below. So we go up 4, and we end up at 0 with a big happy face. Happy face. All right, that will be the end of it. So sometimes with the problem is a little complicated. You cannot do exactly just summation of areas. Sometimes the areas are not as easy. So you go for the equations with all the tools that you learned before. making a cut, you can get the equation of the shear, make the integral of the shear to get the equation of the moment. So with all those three equations, the chuku-chuku or graphical method, cut, and integrals, you should be able to solve any sort of problem of shear and moment diagrams. All right, I guess that's it.